Okay. I was trying to demonstrate this interval here, how it can be used. Rather, how can you scale it down, and how do you scale it up, and why this definition 3.3.1 is going to be very key. So from that, we can generalize. If you have the integral of cosine, this will be 0 for n, but if you look at cos and cos, this is 0. Then you have sine and sine. And for those who may be following, remember when you here, you just have to ask yourself another quick way. If you have an even function and an odd function, so the product of odd and even is odd, then you ask yourself over this interval in terms of an orthogonal set, because it can be generalized. Is it that odd is 0 or it is even 0? We are going to do that shortly before the end of today's lecture, and we will know that, okay, if you are dealing with an odd function, this is what should always be assured. And if it is even, and that will be irrespective of whether you are working with a scaled down kind of interval, that is because this is a full range. And then you may have it as a half range, that is 0 to L. So whether you are working on a full range kind of interval or a half range kind of interval. So here, these are basically just two functions. Here you have one function which is 1, and then you have another function which is sine n pi x over L, which is this. We are going to look at some of these derivations, but specifically with respect to some few functions of interest, especially odd, even. But here we just want to illustrate if you are trying to compute the inner product of an orthogonal set, what would happen within that given interval. And here we are looking at it in terms of full range with respect to odd and even, but for illustrative purposes here, we can now look at this here. So here you have a set of three functions, that is f1 up to f3. So we are saying by the generic definition, which is there we use the phi m, phi n in here. So here we have fn, f, the parameters, you don't have to parameter the notation, it can change. So instead of phi, we have used letter f. So this is the case, and we are saying in this case it is orthogonal. So we need to determine if it is orthonormal, and I think you guys remember very well, since you are dealing with the dot products from your vector calculus, or is it calculus 3? You looked at this, so you have everything here is at 90. You have the I, then you have the J. These are vectors, and then you have the K here. I think you remember. So when you talk of orthonormal, you know that when you dot I with the I, and you always dot, okay, this is I dot I, J dot J, K dot J, that always gives you what? I think that always gives you a 1. Those of you who still remember, then when you alternate them, I dot k, I dot j, and that is maybe I think I've exhausted. There should be 3. You can have this dot that, then this dot that, and then this dot that one. Remember, all of these angles are 90s here. Here, what I'm trying to explain is with the respect to the language. When you talk of orthonormal, you're looking at the angle between the I and the j. So you have x, y, z, but now you look at these as vectors. And once you look at them as vectors, then you have to be mindful of the angle in between, because you can find the angle between 2 vectors. So when we talk of orthonormal here is a language which we are simply changing, as we said, verify whether these 2 functions are what? Are orthogonal. So orthonormal here, we are referring to the 0 that you will get if this situation can be guaranteed. So in this case, just like I have explained here, that you'll keep alternating. For a 0, you can have I dot k, you can have I dot j, you can have I dot j, and you can also have, this was I dot k, we have I dot j, then you can have j dot k. Okay, you have these, and all of these for each of any of those will be 0. And here, the commutativity property works. You can commute these ones. By commuting, even if you have k dot I, here you have j dot I or k dot j. That inner product will still be what? Will still be 0. So I'm using this to explain here why. Here you have F1, you take the inner product of F1 and F2. You can take the inner product of F1 and F3. You can take the inner product of F2 and F3. So that is what I'm trying to explain here, because of this orthonormal kind of situation that we are trying to establish. So just think of the I, j, and k as the F1, F2, F3. So the angle in between is 90, because we are talking of orthogonality. And due to that, then the question is, if I alternate these, will I get that 0? So that's why we take F1, F2, we substitute those functions. Is it a 0? Yes. Then we check. So if any of these is not 0, then we can deduce that this is not orthonormal, or the given set is not orthogonal. Okay. Somebody is saying is not seeing my screen. All right. Okay, I need to verify this. You guys, can you hear me and can you see what I'm doing? Because there is a colleague of yours who seems to be struggling. I don't know whether it's a network on his side or it is a problem on my side. So a quick one just to verify that the problem is not on my side. Can you see what I am doing? Okay, you can see what I am doing. So let me hope, who is this who asked that question? There is someone who was struggling. This is Mr. Sally Badru. Okay, Sally Badru, I wish you luck. Hopefully you will soon see what I am doing. I think you have network issues, or maybe you see the problem with these morning lectures. They are very good, but it also depends on the nature of the bed you have. If you really have a bed and you are sharing it with the fleas and the bed bugs, chances are high the lecture may not be comfortable. One, you've had a sleepless night. Two, as you try to concentrate, you get a bite of a flea. You know, fleas, maybe bed bugs could be tolerable, but fleas, you may find yourself turning, and in the process of turning, you jam the network. So I really hope that this younger brother of mine, Sally Badiru, is in a conducive bed, if I may say. Otherwise, I would advise him to jump out of bed and he finds an alternative. Bed bugs and fleas, this is a problem in Uganda, especially people who come from Makindye, Katoke, Kimombasa. It is a problem. I hope my younger stars, you are not facing these challenges. I hope and pray you are doing fine. Please check out on Badru. Hopefully, is now back. Fortunately, the session is being recorded, so just in case he misses out, I'm sure he'll be able to catch up with us. Apologies, Badru, if your network is still jamming. Let me wish you luck in fixing it. Okay, let's continue. I think this is now really understood, given what we have, given the illustrations I have made. Okay. Yes, so that was to do with the first example. This is when you have an orthogonal set, and I have explained why we keep alternating these functions. And just in case one of them is non-zero, you deduce that it is not orthogonal. Okay. Then we have, these are just some other examples you can go and you deal with, and you check out that. So this is the obvious. Now, in here, there is an interesting example here. For example, on the interval that, can you show that this function is orthogonal to a constant function? First of all, you know what orthogonality means. So you have this function with another function. Is that okay? So if you know function one, in simple terms, I know function. I know one of the functions, and I'm already assured that it is orthogonal. Then can I go ahead and find that function? Of course you can, because you already know by orthogonality it will be 0. You have one of the functions, you're given the interval, then it means you can find the other function. That is basically what we are doing here. So in this case, if you integrate and it is this and it is 0, once you substitute for x from -1 to 1, this is this example here, then once you substitute, you can find the value of C0, and that C0 is the second function. So this one could be changed in terms of assessment, where you simply ask, given one of the functions, can you determine the other function on this interval? Then definitely the definition of the inner product comes through. And once it comes through, punch it in there. And here, this one is incomplete, guys. You can just go and complete it. Since I'm trying to explain this one here, this part here is incomplete. You go and complete it. It has already been integrated. You had the C0 x. So if it is that, since you already have this, substitute the upper and the lower, equate to 0, then you make a C0 the subject. That will be the other function of interest that, or the constant that we are seeking to find. Okay. Then, of course, there are other related examples. Next here, the same story. This is interpretation. Here would we have find a quadratic polynomial that is orthogonal to both 1 and then x. So now when you talk of a quadratic polynomial, since it is quadratic and you are already given x, then you can think of this quadratic form in a general sense. And we all know if it is quadratic, that would be something like a squared. This would be not a squared, but rather ax squared plus bx plus c. This is the generic form of a quadratic function, ax squared plus bx plus c. But in this case, we are trying to minimize the number of what? Of unknowns. So since this is the generic form, I don't have to worry about the constants a and b. Why? Here they are telling us that it should be orthogonal to both 1 and x. So I can, yes, this is the generic form. You remember, you guys, when you did the easy 2, and you are looking for what you would call the particular solutions, YP, and you use what they call the principle of superposition. For you to find that YP, you would first look at the fx. That is when you are solving the so-called non-homogeneous equations or differential equations. Then you find a function that can generalize the one that is given. But given that we have a constant 1 and the x already in the x squared, the x is catered for, then you have one which is a constant. This explicit constant is the c here. So which is the plus c, or you could even use any other constant k. Yes, this is quadratic, that is quadratic. But because we are talking of orthogonality, and here we are given 1 plus x, and the keyword is a quadratic polynomial, then we can take this form. Why? Since we are looking for that otherwise, if you want to include all of these other constants, then you'll have to cluster them, which would bring in a lot of cumbersomeness in the computational part of it. So it's better you take something of a more explicit nature, given that these ones here are already given. And that's why we go for this form. That's why we are saying since x squared and 1 are even functions, it must be the case that they are orthogonal. I think if we talk of even functions, maybe we are introducing this a little bit early, but I can try to highlight what we mean by an orthogonal function, which I had summarized in this narrative. Okay, to change this one. So we are talking of this one here. So for an orthogonal function, rather even function, if you have a certain fx, if you have f of minus x, and you expect 2 scenarios. So you could have f of minus x. Let me put it this way. If you have, this is a curly bracket, if you have f of minus x and it gives you f of x, that function will be even. Okay. And if you have f of minus x and it gives you a minus f of x, this one here is odd. This you already know, I am sure, from your integral calculus. You discussed these things in calculus 2. So if you have this, so why are we talking of these as orthogonal functions? Of course, if fx, if your fx is, what is this? It is x squared. Then we will check out the negative. If you throw a negative here and you square it, you get a positive. So this would imply that the f of minus x, meaning I have minus x, then the whole thing squared. This will give me x squared, which is this is scenario 1. So that is even. And then the one here, of course, you know, if you have plus minus 1 and you square this one here, this one will always give you a positive 1, which is again scenario 1. So that's why we are saying that since this and this are even, then it must be the case that they are orthogonal to x, which is odd. You get that 0. So even and even is even, even and odd is odd. Just like you talk of even is associated with a positive sign, and the odd is associated with a negative sign. So you know that the product of negative and positive is negative, negative and negative is positive. That is odd and odd is even. Then even is even. That is some of the key concepts that we can use to guide in this analogy of orthogonality. So in here, if you've got that, then once you have this, then you have one here. So we are using this to be the generic function for the quadratic polynomial, and then the one here. So the C here is for completeness of the general form of that quadratic polynomial here. Then, of course, if you deal with the integration and you substitute the limits, you realize that the C, the constant C is a third, and then if you have it as a third, then you can substitute and you get the actual polynomial, which is x squared minus a third. Right, the others you can now go through them. It is based on the same analogy. I don't have to dwell much into these others. Now, this is where my area of, now what we have discussed here in terms of orthogonality, this orthonormal behavior, it's going to come in handy with respect to the examples we are going to do next here, guys. So I hope you are still alert with what we just discussed, because we are going to use it right here. Okay. So let's look at the definition. The general definition of a Fourier series. We are saying that you can see the definition is associated with what we have just discussed the other side. So here, be mindful of the series. We are summing from n equal to 1 to infinity. Now, some books, you may find them summing from, I'm hoping you guys are with me, especially the Kuramas. The Kurama may bump into another book with a slightly different notation, and then he will jump around saying he has been given a Katwa. So this is n naught over 2 plus, here we are summing from n is equal to 1 to infinity. The n is equal to 0 has already been catered before in here. Is that okay? So you find that if it is being summed from 0 to infinity, you'll find that that first term is not there, which wouldn't necessarily imply that it is wrong. So you can see here, because we have n1, the n0 is already catered before. If you take n0, that is the n naught over 2. That's why you see that there would be a n here is 0. But in the process of simplifying, you end up with n naught over 2. Otherwise, if we don't want this, we can just maintain what we have here without the first term. We remove this and we sum from n0 to infinity. I hope we are we are together there. Okay, we will emphasize that as we go along, but I'm sure it is okay. So this is the fx. Now, remember I told you all that we are going to do is going to be heavily dependent on the function that we are going to use, because we have a certain function. We have a certain function fx. So by definition of a Fourier, so we are saying, suppose you have f, a function defined on this interval, and it can be expanded in trigonometrical series. Since I started, I've been talking of sine and cos, that is the cos and sine. And this trigonometrical series is going to generate what we call an orthogonal set, because remember, n keeps changing. And here you have this n. So remember, we said if m is equal to n. So you may find this, not find, this may have, this is supposed to be a m cos m pi x over L plus bn. But because of this condition of m equal to n, we have already highlighted that. If you come here, we said we have this. If it is m equal to n, you can get a k. So when we are solving that, we try to avoid the orthonormal part, because if it is 0, then the integral is of no interest, especially if you're trying to find a solution. So to find the actual solution, if you want to avoid that scenario, then we take the condition for m equal to n. So I am emphasizing why in that definition we have only n, yet we should have had m and n. Hopefully you guys are with me. I hope you have understood me there. It is important that you get that. Once you get it now, then my life is going to be easy in the examples I'm going to go through. I don't expect people to ask me, why is it not going, why is it going to 0? Why are we eliminating this? Everything is going to be based on this one here. It is 0 for m not equal to n. So that definition where we have n naught over 2 plus the sum from 1 to infinity of an cos n pi x over L, and then plus bn sine n pi x over L would have been mn, but we are looking at the condition for m equal to n. That's why you find that we have now unified in here. That's why you see this is n, this is n, this is n. Otherwise, this one would be in n, and this one would be in m. But we have m equal to n, and we are going to apply it even down here. That's what we are going. I'm not going to dwell much into this. So you can see in here, when you talk of m equal to n, then you can get this one. Otherwise, if it was m not equal to n, then this one would be 0. That's why we started by understanding the behavior of an orthogonal set, and m not equal to n, that would definitely be a 0. But since it is m equal to n, you have this. This is what you are going to use to establish the nature of the Fourier coefficients. Okay, I was just using that to illustrate 3.4.1. Okay, so since we have this, then the key question here is what is the expression for n naught, an, and then bn? That's what we want to know. And the a naught, so here we only look for 3 terms. And these terms are n naught. We also find a, n, and we find b, n. These are what we call Fourier coefficients. Now, these Fourier coefficients, please please make sure whatever we are doing in this topic here, you don't forget it, because it is going to come in heavily in the PDEs. We have, according to our course outline, we are going to do partial differential equations. And in solving those partial differential equations to find the solution to a PDE, we are going to end up with this same statement here. And then you'll have to go back and know, is it a half range or a full range? If it is a half range, a full range, then it means you bring in the definition of a Fourier sine and a Fourier cosine. And if it is a Fourier, if it is a Fourier sine, which would be now odd, that would imply that you have only an and a naught. Rather, you have a naught and an, the bn is 0. If it is a Fourier cosine, which is even, then you would know that you are dealing with only bn, a naught and an is 0. But for you to get those concepts, you start getting them from these derivations we are making now. So that once you establish you're dealing with a Fourier cosine or a Fourier sine, then there are some coefficients you don't have to worry about. Why? By definition of that cosine, or by the definition of an odd function with respect to a trigonometrical series, it would imply that that particular Fourier coefficient, given the range you are using, is 0 or non-zero. So we are going to quickly bump into a situation where a naught an is 0, and you know, once I am dealing with a Fourier, I'm dealing with a Fourier cosine, I only have to think of a naught and an. Fourier sine, I only have to think of bn. The others are zeros. So you don't even waste time in verifying that. Okay, so given this, I'm highlighting that because that highlight, which we are going to see in the next few minutes, is embedded in what I'm going to explain now here. And surely when I go to that part, I'll simply recall from these explanations. Right. So for the derivations now, I have already informed you that the derivations for these are based on what we have started with up here. That is, should be something you don't forget. The definitions we've done with respect to a Fourier, to an orthogonal set. So going by what we have already talked about, now we can look at this integrating. So what I want now is to find the coefficients, what we call the Fourier coefficients. That's n naught, an, and bn. So when you integrate, this is a normal integration, but here we are going to just stick to whether m is n and whether m is not n. But by the nature of 3.4.1, I've already said here, you are dealing with m equal to n, which gives a k. And in this case, what you are calling the k is that term there. And this term being the case, you simply make n naught the subject, and you get the expression which is here in this carried box. So how did you arrive at this? We are saying if you integrate this statement here, you see this statement here. So integrating this statement, you have the integral from minus L. Please, we are integrating the left and the right of 3.4.1. Let me first decongest by removing the cluttering. Okay. If you integrate 3.4.1, okay, so what you have here, you are integrating equation, this one here. That is from minus L to L of fx, that is on the left. And then you integrate this one here, and you integrate the sum there. So that is L naught over 2, this one dx, and then you throw the integrals in, the properties allow that, and the integral can enter into a summation here. So you have the an, you integrate this function, and you integrate that function. But now what is happening here? What is happening here is once you have this, now here we are saying cos and sine are all orthogonal. And here we have already seen this. Sine, of course, if you try to integrate this from this close the interval from minus L to L, whatever you throw here, this one and this one will always give you a 0. That's why we are saying they are orthogonal to 1. And we have already seen this one here. You remember the example we did up here. We had the cos and okay, there is an example here. This one was from minus pi to pi, but I think we also had another one. We had that one there. And yes, it is here. This one, okay, here it was given in homogeneous form. If you have a cos, you have sine. So here you have 1 and sine, that will be 0. Then you have 1 dot cos. Because if you have only one function sine, then in terms of an inner product, it means the other function is 1. 1 is like silent. This one here. So we are picking it from that once we integrate, guys, I'm hoping I'm with you. I am on this one here. We are applying this one. So we are saying that this is a sine. Remember, in our Fourier, the summation has a sine and a cos. But because it is sine only, cos only, you assume that there is another function which is 1, because you know 1 times this is 1. 1 times that is that. So yes, it is only cos, but you assume that the other function is a 1. But remember, we have already demonstrated that 1 is what? 1 is even. And because of that, that's why you see here, when you integrate this whole term, integrating this integral here will give you a 0 from minus L to L. Of course, the an is there, but 0 times that is 0. And this one here will also give you a 0. Remember, there is a 1 dot. And then here, there is also a 1 dot. Okay, so this term here will basically disappear, vanish to a 0, implying you're going to only remain with this and that. So once you remain with this and that, that is what you get here. Now you have this, which is a naught over. You just integrate this. There is a 1 here. So when you integrate this one here, you end up with your a naught. Of course, you are going to substitute the upper and the lower limit. So the integral is L A naught. Remember, this is 1, integrating that one, you have like x here, then you throw in the upper and the lower. By throwing in the upper and the lower and you simplify, you get this term here. What are we interested in?